The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
So a little bit of a quick introduction. My name is Steven Bryant, and I have been researching relativity theory for about 25 years, mostly as someone who's critical of the theory. And I finished a book in probably 2016 and decided to pivot and follow my passion again, which was in artificial intelligence. So I returned and picked up my master's degree from Georgia Tech in computer science, specializing in AI and machine learning. And through that journey of physics, where I've written some papers, had an opportunity to speak at conferences, et cetera, I will just upfront say I haven't changed the world yet in terms of my view. And what I've learned as part of the Georgia Tech program was some very important lessons about how to connect with the academic community and how to establish credibility and what that needs to look like. And so I found an opportunity, and it was just a random discussion, kind of a class discussion we were having, where a student asked a question about, what do you think are the capabilities of AI in an academic setting? And I thought about that, and I said, that's probably a book on its own. And I'd sleep on it. And when I slept on it, I came back and said, I wonder if GPT-4, because GPT-3 didn't do it, I wonder if GPT-4 had matured to the point where it would answer my physics questions. So I wonder if it would serve as a research ally. And that led to some interactions with Chat GPT and GPT-4 to basically evaluate a perspective of Einstein's equations. And through that perspective, I was able to have it both confirm my findings, which was great, but also find out what some of the pros and cons and limitations are of the technology. So as you both mentioned, right, on the one hand, it's a great ally, and I'm using it as an ally in mathematics. On the other hand, it's horrible at mathematics. So how can you use it as an ally?
Why is that?
So there's actually a large body of research that's going on right now to understand how to make it better, from fine tuning to what I'll call multiple stacks. So you might have a stack that says, give me an answer. And generative AI may not always give you the best answer just because of the way that it works.
Because it's sourcing, because it's kind of just averaging lots of answers? Is that how it works? Or
So great question. Think of it this way. If I was to begin a phrase, roses are red, violets, how would you finish that?
Yeah.
Are.
I mean, blue, I guess is what I'm supposed to say. Yeah.
So right there, you were able to finish the next two words just based on kind of prompting of what I gave you. And generative AI today, in large fashion, behaves that way. Now, and it's based on probability. So when you said are blue, your next word was are. If you had said instead, don't. Roses are red, violets don't. Then you figure out a next word based on that. So there is some probability based into it, but the highest probability would have been the word are, and that's probably what you would have seen. So,
and that's based on the memory, right? That's based on excursions into past versions of this, right? Where I know that because I've seen gazillions of instances of that phrase that's filled out that way. And so I assume the reason that it sucks at math is because it's looking for that exact same pattern, and math is also sort of generative, and so it's not going to have the exact same pattern all the time that you can just source. Is that what's going on?
That's part of it, but also it's been trained to see a whole bunch of different things. So let me give you an example. Let's say I want to negate a value. So we'll call the value A. And I could say negative A, which is its negation, or I could say negative space A, which many people would still view as a negation. However, depending on how it's been trained, it might view negative space A as bullet point A. like in a PowerPoint presentation or Word outline or something of that nature. So now all of a sudden it's confused from that point on because it's looking at A where you intended it to be negated, but from that point on, it did not pick up the negation. So that's one form of a simple kind of mistake that I observed when I was interacting with it. You can overcome it by being a researcher who's meticulously watching what it does. But since I did my initial research, they've also added the ability for plugins. And so the Wolfram Alpha plugin really kind of ups its game for mathematics. And it doesn't make the same type of mistakes, or at least as frequently using that plugin as it does when it stands alone.
That makes a lot of sense. And so what was the process by which you were talking to GPT? What were you asking it to do for you?
Great question. So for that, can I step back a little bit just to tell a little bit of the story of the relativity journey, and then layer that in with the AI journey? Okay, cool. So I want to just talk first about the few elephants in the room, right? So if someone comes and says, I think relativity is wrong, the two elephants are the room are what you're going to hear. One, people have looked at the theory for more than 120 years. No one's found anything wrong with it. What makes you think you found something wrong with it? And two, same preamble, people have been looking at this theory for more than 120 years. It's been repeatedly experimentally validated. So how can you tell me something is wrong when all the evidence suggests that it works, right? So that becomes the elephant in the room, and often that's where the conversation ends, right? Because if you're, let's say, a leader in the physics space, you know, your next question is, who are you? You're not one of my grad students. Where did you go to grad school? You didn't, wait, you're not a physics person, et cetera. And so again, it just kind of through that qualification process starts to eliminate the person who is challenging relativity. So how do you overcome that? And the way to overcome that is you step back, and again, something I learned from my Georgia Tech experience, and you leverage your area of expertise. So my area of expertise is computer science, which is foundational for mathematics. And so if I can stay in my swim lane and leverage a new partner, Chat GPT, which is in the AI computer science space, I now stay in my swim lane and establish a body of expertise. And from that position, now we can have a conversation.
Can we back it up even further than that? Like you laid out the two elephants in the room. What in the world made you disregard those elephants and think that there could even be something amiss?
That's a great question. So I have to go way back now.
Yeah, please. We got time.
When I worked at Accenture, and a few of us, there were four of us who would hang out at lunch. Three of us were named Steve. And his name was Gianni. He was Italian. And we'd sit at lunch and we'd make our fictitious company, three Steves and a Gianni. So no matter what we were talking about, that was our company name. And at one time I said, you know, it would really be good for space travel and this if we could do real-time communication with satellites. So that way something out at Pluto or whatever, you could control in real time. And they said, Steve, you can't do that. And I'm like, why not? Because relativity. And I'm like, or they said, because Einstein said so. And I said, why does he get to make the rules? And they said, well, you need to go learn about relativity. So I crossed my arms and stomped off and said, okay, I will. And so I enrolled in a relativity course. I started to drink the Kool-Aid. I was following along with what the instructor was saying, but I picked up a nasty habit. I'll call it a great habit, not a nasty habit. From my first semester calculus teacher in undergrad. And he would always start with, let's draw a picture. So he would always want to rederive the equation, not have us memorize anything, but be able to draw a picture and derive it. He felt if we did that, it would be with us for the rest of our lives. So I started to rederive Einstein's equations. And I found an equation where on the piece of paper, I had two circles and I had three lines, different lengths for radius. So either I had an extra radius or I was missing a circle. And that was the beginning of my sliding down the rabbit hole to eventually make the discoveries that we'll talk about today.
So what's the significance of the extra radius?
For me, at the time, I didn't know what it was. What, as you'll see today, it's the result of basically there's two time values. And so we'll talk about how and where that is in just a moment. So let's go back to the elephants in the room, right? Einstein's been looked at for, this theory's been looked at for 100 years, and it's experimentally validated. How do you overcome that? I think, to be fair to someone I'm talking to, I can't say anything subjective, right? So I can't say, get into my head, take this subjective perspective. Now the world is this way. That's not fair. It's not going to change the world. To be fair to me, it shouldn't be based on my changing your belief system, right? So it should be completely objective. If we say 3 times 7 is 21, you should be able to objectively go perform that calculation and see if 21 is produced. I don't care what 7 means. I don't care what 3 means. I don't care what 21 means. In order to keep it in my realm of expertise, we can only talk about the math, not the meaning, right? So again, this is very important in terms of that credibility. So if that's the ground rules, then what are the 5 questions we now have to answer to slay those 2 elephants that are in the room? Question 1, objectively speaking, what's wrong with the theory? Number 2, if we buy that that is an objective problem, what's the root cause? Number 3, if we buy that's the root cause, why hasn't anyone found it before? Number 4, okay, I buy the theory side. You're saying something's wrong. How are you telling me that something's wrong, yet it works? And number 5, which is the why should I care question, is show me where relativity makes a failed prediction. Right. So those are the 5 things that if we're going to have a serious talk about relativity, we have to be able to objectively talk about. Now, the first one is what my paper was about, right? So I used GPT-4 as a research ally to basically confirm that first item. Where is there a mistake? And the mistake you can think of as simple as the substitution rule in algebra, right? So if we begin with, let's say A equals B times C, that defines a mathematical relationship that is always true, because if it's not always true, you can't do substitution. Right? It just won't work if it's not always true. So if we say A equals BC, but only if C is 7, otherwise it's not. No, substitution doesn't work that way, right? Substitution says this is an always relationship. Einstein, in his paper, creates a variable, psi. I like to think of it as a cursive-looking capital E. It's a Greek letter. And I got tripped up. A lot of people get tripped up on the Greek letters. It's just another symbol that we'll use for math. And he says psi equals C times tau. And tau kind of looks like a small cursive R. So it's no different than saying A equals B times C. It defines an always relationship. This must always be true. Now, Einstein later on in his paper gives us an equation for psi, and he gives us an equation for tau. Great. Let's plug some values in that equation, in both equations, and see if this equality is maintained. So if you take x equals 1, v equals 0, and t equals 0, just making this up, you can then go to Einstein's equations, and with v equal to 0, the denominator washes out to 1, so you can ignore that right off the bat. If you look at his equations, which are all found in section 3 of his paper, psi, the numerator is going to be x minus vt. Well, we said x was 1, and vt, v was 0, t is 0, so we get 1 minus 0. So psi evaluates to 1. How about tau? Tau in the denominator is still going to evaluate to 1 so that we can eliminate the denominator. In the numerator, we get t minus v x squared over c. Well, let's look at that. T we said was 0, minus v, which we said was 0. And I don't care what the other stuff is because it's a multiplier now. So you get 0 minus 0. So you get tau is equal to 0. So let's plug that into that equation, that always true equation. Psi equals 1 equals c, which is the speed of light, times tau, which we just evaluated as 0. So you get 1 equals 0. That's a mathematical contradiction for an equation that must always be true. That is a failure case.
The DemystifySci podcast is supported by viewers like you. So if you want to help us grow, come on over to patreon.com/DemystifySci. For just a couple dollars a month, you get to help us grow, and you get all of our episodes early on Saturdays, and you have access to our fantastic Sunday patron chat. If you don't have any cash right now, that is totally fine. You can just tell a friend. Word of mouth is one of the biggest ways that we can grow. If you want to participate and get involved in the community, come on over to Facebook, Discord, Twitter, and get in touch with us. Help us come up with new topics to cover, people to interview, and just find a way to be a little bit less alone in the world. Finally, we are planning our very first conference. It is going to be April 6th and 7th of 2024 in Austin, Texas. Tickets are not on sale yet, but they will be soon, so you can just mark your calendar and get ready for that when it is live. In the meantime, back to our conversation with Steve Bryant.
Now, what's interesting about that failure case is that in math, an always true equation, if you have one failure case, that's enough to reject it. But when you have a well-established theory like relativity theory, people will consider that an edge case. They'll ignore the math rule and say, well, that's an edge case. Obviously, it doesn't work because velocity has to be greater than 0 and time should be greater than 0. So you found the one case that it doesn't make sense for. Okay, fine. And this is where in the research paper, GPT-4 was a tremendous ally because it came back with that argument. So I had basically a partner who said, well, this is how the physics community is going to respond to that argument. You are going to need to show that this works for different values of v and different values of t. And so together with GPT-4, we split the space, and you can narrow it down to just look at the x and t values. You can ignore v for all v's that are within the range that we care about. And you get 4 quadrants. You get a quadrant where x and t are both positive, a quadrant where x and t are both negative, a quadrant where t is positive but x is negative, and a quadrant where t is negative and x is positive, where you get 4 quadrants. Relativity in theory should work in all 4 of those quadrants, meaning that equality, psi equals c times tau, should always be true. What we found is you take one of those quadrants where t is positive and x is negative, there is no value of t and x that will ever make that equation true. That whole quadrant is eliminated. Similarly, if you take the quadrant where x is positive and t is negative, there is no quadrant where that equality is true. And this is in one of the pictures. I think it's figure 1 in the paper. So that leaves...
What's the physical significance of negative x or negative t in a physical equation? What does that mean?
So it could mean I started 20 feet behind from where I'm at now.
That's
on a
x,
coordinate system, and I'm at 0 right now, for example. So it's just a number of where you happen to be, or it started 10 seconds in the past. But where you're going is a really important question, because a counter argument could be, I only care about the cases where x is positive and t is positive, and you haven't addressed that yet, Steve. Well, let's constrain it a little bit. Let's not consider all t and all x. Let's just look at x up to 300 million. And let's look at t, let's say above a second. Maybe I think we could say that there's a lot of applicability for x up to 300 million and t anywhere a second or greater. Under those constraints, that equality, psi equals c times tau, is never maintained either. So there is a very narrow line on which that equality is maintained. So that's the first argument that addresses the first of those 5 criteria, right? So I argue that there is something that can objectively be measured. And the way that you can objectively measure is to put those numbers in, as we've talked about, and test that equality. That must always be true because it's part of his substitutions. It is how he creates his psi variable.
By the way, is there a physical attribute assigned to psi and to tau? Do they have a name?
So there is, but I would say, can I answer that as part of the next question?
Yeah, we'll come back to it.
Okay, because I think we will answer that. Because the next question is, so what's the root cause? Why this thing, you see it in his paper, he says, psi equals c times tau. And then you look at the rest of his paper and you do the math, you will not see an obvious mistake. So how does a mistake get introduced when it's not jumping off the page at us? And the question is, I'm going to begin by planting a seed. And the seed is, I'd like you to just write down or think about this equation or expression. It's going to be t, as in Tom, minus, and then you're going to have a fractional part. On the top is going to be t minus s, and on the bottom you're going to have 2. So it's going to say t minus the difference, t minus s, divided by 2. If that's not jumping out at you in terms of what that is, don't worry about it because we're going to come back to it in a moment. I just want to plant the seed. So let's talk about averages for a moment. We all know, and we're going to make it simple. By average, I'm going to talk about an arithmetic mean. So, and it's going to be simple. We're just going to take 2 operators. So, and to make it simple, we're going to say 10 and 8. Right? So if I was to ask you, what's the average of 10 and 8? You'd quickly come up with
9.
9, exactly. From a computing perspective, you would say, I have 10 on my fingers and thumbs. I have 8, and the answer is 9. So all of those can be represented on my hands. Let's do the math the way most people do it. 10 plus 8, I'm out of fingers. In computing, that's called an overflow. And overflows are bad. If it causes your computer to crash, that's a good thing. What you don't want is it to go 10 plus 8 is this, divide by 2 is 4. That's a very nasty bug to try and find. So if it didn't crash and it's giving you a result, those are brutal. So computer scientists have to think about how things are represented, because if you have a 16-bit machine, a 32-bit machine, a 64-bit machine, there's a maximum number that you can represent in that bit configuration. And if you start to do addition or multiplication, you can get a number that exceeds that range, just like adding a digit when I have 10 exceeds what I can represent on my hands. So you fix that by changing the equation. So let's go back to that equation that I gave you earlier, which was t minus, on the top was t minus s, and on the bottom was 2. Let's distribute that negative sign in. So you will now get t minus t over 2 plus s over 2. We can group the t terms together. And just like if you had a full cup of water and you poured out half a cup, we have a full t and we take away half of t, we are left with half of t. So the equation is now t over 2 plus s over 2, which we can group together and say t plus s, that sum, divided by 2, which is the equation for the average. So what I showed you earlier was that equation for the average. And it was just in a different form, but in a form that doesn't readily jump out at people. It doesn't scream, I'm an average. So let's see how we might use this average equation. And then this will get to the question that was asked a little bit earlier. So let's imagine a bus. And this bus is on the street, and I'm going to pick on my niece for a moment. Her name is Charlotte. So, and I like to say, working with 5th and 6th graders, so she's about that age, so I will just use her as my example. So Charlotte's at the back of the bus, and we're going to task her with a job. She's on the street. Her job is to go from the rear bumper of the bus to the front bumper of the bus. We're going to measure that time. And then we're going to ask her to go from the front bumper of the bus back to the rear bumper of the bus, and we're going to measure that time. We're going to say Charlotte travels at a constant velocity to make it simple. So we do this experiment. We come up with the amount of time that Charlotte, and the bus is not moving right now, so we have a baseline on the amount of time for Charlotte to travel that distance. So now we complicate this. We put the bus in motion, not so fast that Charlotte can never get to the front of the bus, but it's in motion. So now Charlotte has to still go from the rear of the bus to the front of the bus, but because the bus is pulling away from her, it takes her longer. Now, when she's at the front of the bus and we asked her to turn around and run back to the rear, she's running towards the rear, but the rear is also approaching her. So that amount of time is shorter than the baseline amount of time. So we will have what we'll call a long value and a short value. So if you have a long value and a short value, going back to 10 and 8 as our examples, you can say there's another way to find the average. And so if t is the long value and s is the short value, you could say t minus s, which was 10 minus 2, 10 minus 8 is 2, divide by 2 is 1. And I subtract that from the big value, which was 10, I get 9. Again, you found the average, just using that other equation that I gave you. This bus example, when I say what's half the distance, what's the average distance that Charlotte has run, you would find those values and you do the same thing. You could either add and divide by 2, or you could do it this other way. Here's the thing. Let's give this example some meat now. We need to give variables in place for things. So the bus has a length. The length of the bus is x prime. Charlotte has a velocity. Her first name starts with C, so we're just going to use the letter C for Charlotte. And the bus has a velocity as well. That's v. So when Charlotte is moving from the rear bumper to the front bumper, the equation is x prime over c minus v. That's the amount of time it will take her to get to the front of the bus. And you could multiply that by c to get her distance. Likewise, if she's at the front bumper coming back, it is x prime over c plus v. And again, you could multiply that to get the distance. So the question is, if I find that average time, and then I multiply it by c to get the distance, what's that equation? Interestingly, the equation is also found in section 3 of Einstein's paper. It is x prime c squared in the numerator, divided by c squared minus v squared in the denominator. And he sets that to psi. So going back to your question, in my interpretation, when you say, what is psi? What does that represent? It is 1/2 of the distance of oscillating that moving system, so to speak. So just like Charlotte had to run, she was on the sidewalk, but we asked her to do something with respect to the bus. We got 2 measurements. We found her average. Einstein finds this average, which is easy to confirm by just taking those 2 equations, adding them together, dividing by 2, and multiplying by c. Now the question is, so where does he do this equation? Because you can look at his paper, he doesn't do that math. But what he does do is the equation that I gave you up front, the t minus the difference t minus s over 2. And so this is where it gets really, there's a cool part here, and I'll just tell you what the cool part is. If you take t and s and you add them, so you take the sum and divide it by 2, and t and s are those 2 equations I gave you, you will get x prime times c over c squared minus v squared. If you take their difference, the only thing that changes is that top c changes to a v, which is really cool if you think about it. That's the difference or the sum. The only thing that changes is that c changes to a c, the c changes to a v. But what does this mean? Now, if you look at his tau function, which is all this, he does this partial differential equation, etc. You look at his tau function, you have t minus that equation that I just gave you, that half the difference, and which is v squared or v prime, x prime v over c squared minus v squared. So, but that's in his paper, so you see it right there. Now,
I
the
guess
thing about
all that
this-
means is that two things that are moving, you can compare their relative speeds to one another, something like that.
Well, what it means is when he does his next step, when he finds I, and he says replace t with x prime over c minus v, he has now completed the equation for an average. So he has used the other form, that alternate form of an average, and he simply found the average distance found. Now, what's important here is to notice, we've talked about averages. I'm saying, again, objectively confirmable, right? You can go to his paper, you can do the math, you'll see the same equation. We haven't invoked simultaneity. We haven't invoked time dilation. We haven't invoked length contraction. None of this was needed to show this math. Now, one other part that I think is interesting here is, so Steve, you told me the average, but where you said there was two time equations going on, and that was why these two things happen. So keep in mind, there's a standalone tau equation for time, and then he says psi equals c times tau. So there's a tau equation right there. The thing is, in the tau equation where he says psi equals c times tau, he does that replacement of t with its value. Whereas in the top one, the standalone version, he does not.
Sorry, are t and tau the same variables here?
Oh, I'm sorry if I'm saying the wrong thing. So tau is the transform time, and t is depends on how you use it. The way it should be used is how he uses it with psi, which means it's the long value. He replaces it with x prime over c minus v. And again, he says that replacement in his paper. In his standalone tau, he does not make that replacement. And that's why we get two different values for tau. And that's where that inequality is introduced.
So basically, after this replacement isn't made in both of the equations, that's where you get the source of the difference. Because when
Bingo.
you go back and you start plugging things in, you find that they're not actually substitutable.
Bingo. That's exactly right. And so again, this is a conversation I've had with Chat GPT, not in this paper, but in just additional research. And it's basically confirmed that, yeah, this is a mistake if you don't do that replacement in both places. So it's really nice that this research ally, I'll say Chat GPT with the Wolfram Alpha plugin, is yielding that same thing. So that answers part 2, what I felt was the root cause, and 3, which is why it hasn't been seen before. Because if you don't recognize it as the equation for an average, and B, you don't recognize it as that equivalent equation for an average, why would you even consider it to be an average? Why would you even go down this path, right? So
what is the average of?
So to keep it, I'll say it in kind of concrete terms, and then we'll make it abstract terms. So concrete terms, we have a bus, and we have Charlotte. Charlotte ran one distance to the front of the bus and another distance to the back of the bus. And we said, what's the average of those two distances that she ran? If we generalized it, we could say that bus is what Einstein would call a moving system. The road is what he would call a stationary system. And in his case, he doesn't have a niece named Charlotte. He has a ray of light that's moving at a constant velocity, albeit a faster constant velocity than my niece. But the math still applies. When we're talking about variables, the equation, when you're solving algebraically, it doesn't matter what value C holds. That only matters when you decide to tie it to some sort of theory or some other application.
But the averaging is aimed at giving us ultimately the length of the bus?
Yes, the length of the bus or the speed of light?
It's actually telling us the ray of light had to go one way to the front of the moving system, one way to the back of the moving system. It's basically saying, on average, how far did that ray of light travel? If you think of it in terms of
but we're trying to measure the bus, right? Is that what we're trying to do ultimately?
No, see, that's the thing. Okay. When we talk about physics and relativity, they then take this equation that is applied to Charlotte, right? We're talking about Charlotte, but then they will relate that back to the bus. And by saying it's the equation to the bus, that's where concepts like length contraction come into play. Because in this view, something is important. You still retain the Newtonian equations. Charlotte is moving according to Newtonian equations. The bus is moving according to Newtonian equations. We're asking a question that just is, how far did Charlotte go on average, right? There's nothing relativistic about it. What happens is if you say, I don't have a Charlotte anymore, or in relativity's term, by definition, when you go halfway, you are at the front of the bus. Again, that's an assumption for relativity. I think it's the principle of relativity. So that's where that comes in, and it applies to the rest of his interpretation of the math. But in my interpretation, we're asking a question about Charlotte, or in the theory, we're asking a question about the ray of light, the wave of light, the particle of light. We're not talking about the bus or the moving system.
Okay, so let me see if I wrap my head around this correctly. You're basically saying that when you have a system where Charlotte is running from the back of the bus to the front of the bus, and the bus is stationary, you can make statements about both Charlotte and the bus based off of the time that it takes for her to get from back to front and back again. But when you start to move the bus, you suddenly start to change the amount of time that it takes for her to get there and back. And when you get the average, you have to be careful to understand that there is motion in the bus that is causing a change in the time that it takes for her to do the run. And if you're not careful and you end up with Einstein's conclusions about relativity, you conclude that the bus has shrunk, as opposed to the fact that the bus is moving, and so it takes Charlotte less time due to the fact that it has now become a dynamic system rather than a stationary system.
That's very close. There's one point I'm not sure I heard that I want to just clarify. Yeah. And it's, in this case, Charlotte's not on the bus. She's on the street. Right? So when we say it's going to take her longer to run from the rear bumper to the front bumper, it will, because the bus is pulling away from her. Right? So we can say now she's finally reached the front. How long did it take her to do that, or what's its distance? Then when she turns around, she's going to run a shorter distance than baseline because the rear is approaching her. And again, we now have two lines of two different lengths, and we can just say, what's the average length, right? Okay. On average, how far did Charlotte travel? Or on average, how far did this ray of light travel?
But if you are uncareful in the way that you analyze that, what you end up with is that the distance has
when Charlotte turns around and runs back the other direction, she experiences some length contraction of the bus. Is that what you're saying?
Yes, because that's the relativistic conclusion of this, right? That there's some kind of length contraction when you have a stationary system and two moving objects. And so if you're not careful in the assumption that so 1 second, let me take a step back. If Einstein's math didn't have an error in it like the one that you found, then the conclusion that he makes could potentially hold because the math holds and it's just a weird oddity of reality, and here we are. But what you're saying is that the equations that he uses to make these conclusions are missing a certain internal consistency, and so the mathematical conclusion doesn't hold, therefore the second order philosophical conclusion cannot hold either because the math doesn't hold water. And so we have to rethink the entire basis for these relativistic strangenesses because the math isn't internally consistent.
Absolutely. And you're hitting the nail on the head on a very important point, which is if the math is consistent, which I argue it is not, but if it is consistent, Einstein was first. So he gets to define the interpretation. So if someone says Einstein's wrong and they don't challenge the math, but I want to challenge him because I don't believe in the twin paradox or this or that, it's too late. That ship has sailed. He defined it, so he gets first right of defining what it means. We only get to change that if its math isn't right. And that's what I'm saying. And again, this is not to change someone's belief. This is to say, objectively sit with his work, take it to Wolfram Alpha, take it with a pen and paper, work the equations, and see if you get the same answers as I get. And if you do, then take the next step in that series of questions.
Do you think that you'd have an easier time if you pointed out that it was Minkowski who did the math and not Einstein?
You know what? There's a lot of debate in terms of who actually did Einstein's math. And I think it's there's some parts of it that are just absolutely brilliant. I'm critical of his work, but I think what he contributed in terms of how he approached things and just sparks of brilliance throughout. So nothing I say should take away from that. But he's human. And as a human, we could all make mistakes. And so this is just one of those cases where if we've made one, then let's correct it and position ourselves for wherever we go next in our scientific discovery journey. Right. So,
and then maybe reassess the interpretation. It's interesting you said that there has to be a fundamental fraction in the math for the interpretation to be shaken, because there are a few tantalizing examples where that wasn't the case. My favorite being heat, right? Because fluid dynamic equations describe the transfer of heat really, really well, but it's totally wrong, actually. It's not a fluid. And it was treated like a fluid, and they actually did a lot of work on these early thermodynamic engines using those equations. And they work. It allows you to make devices, and it's fantastic. But ultimately, some experimental evidence piled up to the contrary, where they weren't able to generate endless quantities of this fluid. They were able to generate endless quantities of this fluid by basically applying friction to the system.
It was a cannon borer.
It was cannon boring, I believe. And so every once in a while, it does turn out that the math is okay, but the interpretation itself has to be revisited. I think it's just much more difficult when you have some, demigod, some like huge monolithic mythical character like Einstein, whose face is in every single 6th grade math classroom, or you're really, really fighting an uphill battle if you try to challenge anything about that.
That's right. And you're right about the interpretation as well.
And I assume that plays in, by the way, into how something can work but still be incorrect. That's like step 5 or step 4 or something. We'll get to that. Yeah.
Well, let's talk about that.
Cool.
So we've talked about what I thought was wrong, which was psi equals c times tau, an always relationship that when you actually test it isn't always. The root cause, because when he simplified his standalone tau equation and his psi equation with the embedded tau, he did that in 2 different ways. And number 3, why didn't we see it? Because we didn't recognize it as an average. And even if we did, we didn't recognize it in this format to really analyze what was going on. So those would be the first 3, objectively stated. And the 4th one, I'm going to give you an example. So when I was about 10, I'm dating myself here, this would be somewhere in the early 70s, my dad came home with a Casio calculator. And this was, home use calculators. And I know for folks nowadays, it's like a calculator. I just have my cell phone or whatever. But at the time, it was a big deal to have a calculator in your house. And this calculator had 6 digits and it was all integer digits, unless you took this little toggle switch and you slid it to the side, and then it would give you 2 digits of accuracy. That was it. No more. 2 digits of accuracy. So it was great for balancing your checkbook or something like that. But, if you're trying to land a lunar lander on Mars, it's probably not what you want to be using. So let's say that someone comes up with a theory. Someone walking along, they say, I have a theory. And it's before a theory is established. They say, I believe pi is 22 divided by 7. Okay, it's an interesting theory. Can you experimentally validate it? Sure, I have this calculator here, my parents' old Casio. Let's try it. 22 divided by 7. Answer, 3.14. Bingo, that's exactly what we should expect, 3.14. Perfect. So now we go around broadcasting pi is 3.14, which is 22 divided by 7. In fact, I think I learned it as a crutch, very, very young age, that pi you could find by 3.1, divide 22 by 7. But it's not. And so someone now comes along and says, I don't believe that's right. I think I have a better theory. I think the theory is the circumference of a circle divided by its radius. And so Let's try that. And you key it in the calculator and you come up with 3.14. Same answer. So you know what? 22 divided by 7 was here first, so it's the prevailing theory. I have no reason to be motivated to do anything else. The only way to know for sure is to understand how did we come up with our expected result and our actual result, and what does the experimental device measure, right? So our expected result, we said, was 3.14. Can we tune that better? So mathematically, you might write it as a series, and I'm going to do it as a simple series, 3 plus 0.1 plus 0.04 plus, et cetera, et cetera, et cetera, right? And I could do that for both theories. And if I, depending on where I draw my horizontal line and truncate the rest of that, if I drew the line 3.14, draw the line, I can't differentiate my theories. But if I went 3.14 and went a few more digits and drew my line, maybe now I can differentiate my theories. Okay, so great. I have a way of differentiating my expected result. How about my actual result? Well, sorry to say, Mom and Dad, but the Casio calculator just isn't going to cut it. So I'm going to go out and buy my new HP Prime calculator and run it through that. And it gives me enough significant digits so that I can at least go up to where I've now cut off things. So that is interesting, because now when I run the experiment, I find that the person who was saying circumference radius thing is more accurate than the person who said 22/7. Okay, maybe I do need to change. So we can now say 22/7. Some people might go so far as to say it's wrong. I would say it's right to a point, and then it becomes wrong. So how does that apply to relativity? And for this, what we really want to look at, we won't go into all the math, but we look at his derivation of E equals mc squared. Very famous, very well tested, very well researched. But when you look at that, he builds a series. He basically says this plus this plus this plus this, and he has different terms where you have, c squared, c to the fourth, c to the sixth, c to the eighth, etc. He chops it off at basically c to the second, which is where you get the mc squared from. So he doesn't show the c to the fourth term, c, etc. There's another set of equations that start with the exact same first term, but then in later terms, they differ. But he chopped them off, just like we chopped it off at 3.14. So at that chop off point, there's no way that you can differentiate Einstein's theory from another theory, different equation, but where it's been chopped off, it will now make the same prediction. So 3.14. The only way to have more accuracy is to look at Einstein's equation pre-truncation, look at the alternative equation pre-truncation, and have an experiment that looks at more significant digits to see which one is more accurate. So the argument is that it is accurate to a point, at which point it becomes inaccurate. And the research that I did on that was the Ives-Stilwell experiment, and it did confirm that the alternative equations outperformed Einstein's equations. So by performance, objective measure is going to be the difference between the actual result and the observed result. And so that error is how we would assess the objective quality, if you will, of the result. So that's number 4, right? That explains how something can work and still be wrong, right? Just like 22/7 is not pi, but it works up to a point. So this takes us to number 5. Okay, Steve, so you've shown me that it works, and yeah, you may have some alternatives, but if it works, you're still not going to motivate people to switch. It works. Why? And there's a lot of reputation and money and prestige at stake. Why should they switch? Where's the failure case? Is there an experiment? And how are you going to have a failure case when you're telling me your model predicts nearly identical results to his model? Not always. And for this, I'm going to ask you, I'm going to try and stay away from the math and just go with a little bit of conceptual understanding, right? So if I have a flashlight, a laser light, that laser light sends out a beam of red. So red has a certain frequency. We're going to call that frequency F. If I had a different laser and it shot off green, it would have a different frequency, right? That's just how visual wavelengths works. Interestingly enough, the range of visual acuity is a pretty small area of bandwidth. So if I said that red was F, and then I said, oh, I want you to now look at this new frequency that is 2F, it's outside of the range of what we can see. You just can't see it. So let's do an experiment. The moon is just a little over 300 million meters away. So for sake of our conversation today, let's say that the moon is exactly 300 million meters away, actually 298, blah, blah, blah. However many meters light travels in 1 second. I'm just going to round it to 300 million. I'm going to put myself at risk here, and I'm going to take a spacecraft and go to the moon. so I'm on the moon, and I'm holding a mirror, and you guys have that laser with the red laser beam, and you aim it at my mirror. You turn it on, the laser light starts to travel. 1 second later, the first part of that laser is hitting my mirror. If we could freeze space and time right now, just freeze it, just completely freeze it, we could ask some questions. We could say, how many cycles of wavelength are there between you and me at this moment in time? Well, because I've set this up in a specific way, we know there's F cycles because we've made the distance specific. What wavelength do you see emitted? F. What wavelength do I see? F. Okay, great.
I guess 1 over F technically, or CF.
Sorry?
Wavelength and frequency being inversely proportional to one another.
Yeah, they are. I think I went.
Just saying.
How did I do it?
Anyway. No, I think that you just said that we were seeing the wavelength of F, but it would be 1 over
the frequency of F. Yeah, you're right. Yeah, I'm
Shiloh's
just saying I'm awake here. That's all.
I need to slow down too a little bit. So now time is in motion again. It reflects off of the mirror and comes back to you. And as soon as it comes back to you, again, we freeze time and we count cycles. So there's F cycles to get to the mirror. There's another F cycles to get back to you. So if we're able to count cycles, there are in fact 2 F cycles in this journey. What frequency do you see when it's beaming back into your eye? You see F. You see a red light still. And we know that when we look at the Michelson-Morley experiment, they bounce things off of mirrors. They don't go 300 million meters like we did in our example, but they bounce things off and they come back and they see the same color wavelength. They don't see a different color. So that means we know that what they're looking at is somewhere in the order of F, not 2F. But when you look at their equations, and just set it up for velocity v equals 0 to make it easy, you'll see that their expected result is 2F. So their expected result is incorrect. So how do you change it? You go back to what we were talking about earlier. You take the average, because that's what we're finding for wavelength. And actually, according to my physics books, that's what you would do when you combine wavelengths is you take their averages, or frequencies, you take their averages. So we take the average, and as with our example with Charlotte, there's one additional adjustment. We asked Charlotte to go to the front of the bus and to go to the back of the bus. That's a round trip journey or an oscillation. But when we used our math, we used x prime, which was only half of that. So you have to use half. So you make that adjustment, and then you take the average, and then you analyze the data that's provided in their paper. So you don't change any of their data. You just revise the equation to be consistent with what we've been talking about today. Their experiment produced 30 kilometers per second, which is what they expected to find, which is very different than the 0 kilometers per second that is required for relativity. Okay, Steve, that's great, but you probably force that, for sake of your story. Well, the good news is Miller in 1933 did the same experiment, and he did it with a device he felt was going to be more accurate. And so the Michelson-Morley result was around 6 kilometers per second. They dismissed that as experimental error. His was around 11 kilometers per second. They said, you must really be off because you're not close to 0, nor are you close to 30. So you're kind of wacky. But when you evaluate his data, which is also provided in his paper, using the same revised equation, you get 30 kilometers per second. 2 different experiments, both with the same result, which is very different from the relativistic view. 2 experiments. And then think of this for relativity to claim support of Michelson-Morley. There's 2 things you have to do. Michelson-Morley said, we expect a result of 30 kilometers per second. You have to say, nope, throw that out the window. Michelson-Morley said, we found a result of roughly 6 kilometers per second. Nope, throw that out the window. You really got 0. And lastly, in math, when we are looking at an experiment, in order to know what range of values something might be in, we look at p-values or confidence intervals. And when you look at those experiments and you put a range around what they found, 0 is not within that range. So you basically are saying, I'm going to say that the experimental device wasn't good enough, so I don't believe the expected result. I don't believe the actual result. I don't believe the experimental device. So how does Michelson-Morley support relativity when you've just rejected everything about it?
Yeah, so I think that we should take some time to unpack this because we've really come up against Michelson-Morley as being a foundational inflection point in everything that happened in physics for the last, I don't know, it's been 130, 40 years since they did it. They did it in like the 1880s.
What was an inflection point in the 400 years of physics before that? Too?
Well, it was, but that was what is pointed to as the legitimate moment where the relativistic, mediatorless, disconnected from physical reality physics was able to take over. And so we've spent a lot of time just trying to recreate the mindset that allowed it to be so effective, because it seems wild that you could have an experiment that lets people get away from a mediator. And I wonder if you have insight into why it was accepted even. Because if you come up with an experiment like that and the conclusion is something that doesn't make any intuitive sense, it's something that overturns 400 years of history, then in my mind, I would be like, well, we didn't set up the experiment right. We didn't analyze the data right. We've clearly not gotten to the bottom of this row. We have to keep going and figuring it out. But it seems like after Michelson-Morley, everybody was kind of like, I guess there's no mediator. How weird.
So part of their experiment is we have to recognize when in history it occurred. And so when we look at their paper, I mean, you've heard me already trip over my tongue when I've said wavelength versus frequency, et cetera.
I actually realized that I didn't understand that it was a 1 second travel time. So I understand now why frequency would be equal to the count of waves inside of that distance now. So I think you were right. I just didn't catch the 1 second travel time thing, but it all makes sense now. Sorry.
Okay.
It wasn't your fault. It was my fault.
Awesome. But here's the thing. If you look at their paper, they talk in terms of pencils, right? They don't talk in terms of frequency. Hertz wasn't defined as a standard until the 30s or 40s, maybe somewhere in there. I'm not sure when. So there's things that we now take for granted in terms of how we understand wavelength and frequency and so forth, that they were just on the forefront of discovering. And so it's not clear to me that they would have even thought this needs to be averaged versus added or something of that nature. So, and when they found stuff, they were getting measurements. And I will admit that when I first started looking at their work, I was throwing it all in a spreadsheet and color coding things and whatever. And I could see through my color coding, I could see there's data. I could see there's something there. but it wasn't jumping out at me in terms of what exactly was going on. And eventually it landed that their equation wasn't the right equation. And for the reasons that we've just talked about, and again, it's easy to confirm because just set up the case where something is a second away and give it zero velocity, you will see that they are expecting 2f back in terms of their value. Their device is incapable of counting frequency. So there is no way that they could capture 2f in terms of an expected result. So coming back, their expected result with zero velocity would have to be f.
And that means a stationary ether situation. What is the physical significance of a zero velocity in the Michelson-Morley?
It would reintroduce a positive finding of their experiment of 30 kilometers per second would retain the ether. That's absolutely right.
So I'm still a little foggy on this. Do you want to take a stab
I'm
at
trying to
putting it
catch
in
up,
your
yeah.
words?
So I'm just trying to understand. So you're saying there's these two cases. There's two cases with respect to the possible outcomes of this experiment. One should result in double the travel time, and you're saying one where there's no travel whatsoever is also not found, and neither one of these cases are found.
Oh, I may not have said that right. So I was making a simplifying assumption in terms of the base case. So I was simply saying, if we assume, what should we expect to see if there were no velocity? We would expect to see the same frequency that we sent out, we would expect to see without any shift whatsoever. So if we sent off f, we would expect to see f back.
Yeah, but what is that? What do you mean no velocity? Does that just mean that the Earth is not moving with respect to some ether?
Exactly.
Gotcha.
Exactly.
Gotcha.
So if the Earth was perfectly stationary and we put something out there, we should expect to see that same frequency back, no shift. Their equations say you would see a frequency of 2f. And that's counting cycles. And so we understand how they came up with their math, but that's not what their device is capable of measuring.
I see. You're basically saying that they made a mistake in how they constructed their equations, where they reported observed frequency as total count of frequency in the round trip.
Bingo. Exactly.
Interesting. And nobody's caught this yet.
It's hard. And I think also keep in mind a couple of things when it comes to this type of research, right? If you are a student and you say, I want to enroll in a PhD program and I want to prove Einstein wrong, being accepted to a PhD program is very different than a master's program. You have to have an instructor select you. That instructor is likely to say, I'm not wasting my time. And someone who thinks Einstein is wrong goes back to what we said at the beginning, right? It's been looked at for 100 years. No one's found anything. It's been repeatedly experimentally validated. Let's say you get in, though, and then halfway through you say, I'm now going to challenge relativity. You still have to get that through your thesis committee and so forth. So odds are it's very hard for someone, unless they have a passion or something else, to spend time and dedication to do the persistent deep dive that could be required to look at some of this stuff. I'm not saying it's impossible.
We actually had a friend who tried and he ended up getting driven out of the PhD program.
Mm-hmm.
He had a problem with the pseudo tensor, and he claimed that it was an invalid mathematical simplification. And I think he's got a good point. I'm not a mathematician, but yeah, shout out Steve Crothers. But he got driven out of his PhD program for it.
Yeah, exactly. It's hard. It's really hard. So I think finding the people who are passionate about it, and then I'd say persistent, and then able to go find the information they need, just like any PhD researcher would do, right? You don't necessarily go in knowing everything. You go in knowing how to find what you need so that you can then synthesize it and make sense of it. And so I think finding that group of people kind of narrows down the space, because keep in mind, it's not just the space of smart people. It's the space of interested people who believe there's something there and are willing to invest their time going looking for it. And that narrows the pool quite a bit.
What's this later experiment? You said it was the Miller experiment that you reanalyzed the data?
Yes, so Miller he did an experiment in 1993, also an interferometer experiment. And in that experiment, he said, I want to have a more accurate device. I think that the problem with the Michelson-Morley experiment is their device wasn't accurate enough. So if I can make a better device, I'll get a more accurate answer. Everything's great. So he ran his experiment. He collected his own data on his more accurate device, which was bigger. And when you ran the numbers through the original equations, basically the same equations that Michelson-Morley used in the late 1800s, he came up with 11 kilometers per second, roughly, which is further from zero. So it's further from relativity. And even if you claim it's more accurate, it's still pretty far from 30. So there's nothing here. I don't know what you're writing a paper about. So a lot of people kind of dismissed his work because it didn't support relativity, nor did it support a kind of an ether alternative. It's when you look at his data and interpret it through those revised equations, the same equations we've talked about, that you'll find that he's actually closer. He's like 29 point whatever. So when you compare it to the known velocity of the Earth, he is actually closer than in terms of actual versus expected result. His error is smaller than the original Michelson-Morley experiment. So by that criteria, he was successful. He not only confirmed the result, but he did so with more accuracy.
Is he still alive?
I don't believe so. That was conducted in 1933.
Oh, 1933. I thought you said 1993. And I was like,
Oh,
that's
sorry
weird.
about
That's
that.
so late. No, that's fine. That's too, I mean, so if he got so close and you can look at it, you can look at Michelson-Morley as well, and you can show how the math, when revised, gets you closer to that 30 kilometers a second number. What falls, right? So if there is a stationary ether, what happens next?
So a couple of things. I think when we look at theories, we basically come back to what is foundational. So we come back to the Newtonian equations are not superseded and replaced. We come back to um, a new understanding based on this oscillation motion, this averaging on how wavelength is behaving. And there was a gentleman, I forget his name now. I wish I could remember it. He owns a lot of he's since passed away. He did a lot of patents in GPS space, et cetera. And he was also critical of relativity. And with all of his patents in GPS, et cetera, he said, you know what? All the stuff that we do in GPS, none of it uses relativity. So so a lot of people will rely on that. Yet here's someone who was well versed, well respected in that space, and said it's not here. So I think that there's other math that people are using today, like he was using in GPS, that will just be a little bit more pervasive. And at some point, we have to revisit. So, what is there anything that we retain from relativity, either conceptually or not? Or is it that we do a reset back to classical mechanics and go from there? Because even something like quantum mechanics, you could say, well, that's incompatible with relativity. People have said that. Okay, well, if you don't have to make it compatible with relativity anymore, does that open the door for us to even do more creative things in that space?
Yeah, that would be exciting because quantum mechanics is also really missing the mechanics part of things.
There's a lot of probability in quantum mechanics, and
interestingly, that was something that really disturbed Einstein, from what I understand, from reading his correspondences and debates and letters.
Exactly. I mean, it depends on your point of view. Again, if you're one of these who is A always has to equal B times C, then that's going to bother you. But if you are, and if you're working with, for example, large language models and transformers, and you have to deal with probabilities, then maybe working in that probabilistic space, you're a little bit more comfortable.
What have been people's reactions as you present this work?
So it depends on whom, right? So there's going to be a large amount of people who are, as I mentioned at the front, who are you? It works, and it's been looked at a zillion times, so we're not even going to waste our time. There are, and some of those may have deep backgrounds in physics, others may not. I've been fortunate enough to meet some people in the physics community with deep backgrounds who have been very open. One helped review my book. So there's a lot of people who, if you reach the right person, are open to it. I'm part of a community that allows some of this type of conversation to flourish. Sometimes you get some great conversations. Sometimes you get a lot of subjective ideas out there, but at least everyone has a chance and you get to see what's out there. Sometimes they do conferences standing alone. Sometimes they partner with organizations like AAAS, et cetera. So I've had a chance to talk at a few conferences at universities to present this as well. What I found is that that's been a slow road, mostly because, again, goes back to the beginning where I talked about credibility. That's not where I immediately walk in the room and have credibility. What I think has been a game changer, and I think is an important game changer for anyone who's looking at multidisciplinary research, is the partnership with generative AI, because I'm staying in my swim lane. We are not talking about the theory is wrong because time dilation or because the twin paradox or because we didn't need to invoke any of that to talk about math. And when I worked with GPT-4 as an ally, I enforced it to stay with math. And so I'm staying very well in my swim lane. And by staying in my swim lane, hopefully I'm saying something interesting to people. So it's an interesting story. But then I'm hoping that there's also value in terms of people who then read the paper and go, here's some guidelines and some limitations based on what this one researcher found in working with GPT-4. How do we now overcome that? Either as a researcher trying to make large language models better, or as a researcher who's just trying to do new novel research and want to use it as an ally, right? How can I get the most out of this tool? If I know it makes math errors, how am I going to get the most out of it and build trust that it's telling me something that isn't going to come back to embarrass me later, right? So one, find a mathematician if you're not that person who can review everything. B, give it a plugin like Wolfram Alpha, which is a very strong math engine, or figure out whatever it is you need for whatever domain that you're doing. So I think, to me, the game changer is this artificial intelligence, somewhat claim the seeds of artificial general intelligence, as a research partner. Because now it's not just Steve Bryant making a claim, it's GPT-4. And if someone wants to claim GPT-4 is wrong, they can. But you're not battling Steve Bryant anymore. You're battling OpenAI. You're battling, a whole bunch of other smart computer scientists who are saying, we think this has artificial general intelligence properties. Let's kick the tires and see what's going on. So if at anything, regardless of whether what we've talked about earlier is true or false, I hope that it becomes a foundation for saying, if it's wrong, then we need to go fix GPT-4. And if it's right, then boy, GPT-4 was a great research ally. Let's now start to advance not only physics in this moving systems domain, but where else can we leverage this tool and see what else we might be able to unlock?
And that's kind of what I'm curious about. I'm wondering, has there been anyone who has looked at the analysis and has offered a cogent criticism? Right? Because I know that there's always knee-jerk responses, right? Who do you think you are? Do you think you're smarter than Einstein? We have the physics. Everything is settled. I come from a family of engineers, and engineers, I think, are the worst at this because they're basically like, why do we need to change this? The equations work. Look at all the things we can build. And that's a very, very difficult point to argue with because they're right. They do work. You have GPS, you have cell phones, you can buy a grill with Wi-Fi. Like, it's everything that you possibly could want, modernity has provided. And so it seems absurd to say that the fundamental mathematics of physics over the course of the last century are somehow flawed. And so I wonder if once you get past all the knee-jerk stuff, if there's been anyone that has offered a legitimate reason that this might not be right.
Not yet on this argument, right? So through my journey, I've had different incarnations of the argument. So one of my early arguments was there was an equation that didn't quite work right. And someone will say, well, that's because he's talking about a point, not a circle, and say, or whatever. And so I'd say, okay, well, you have to look at it this way. And then there would always be an objection. And what I found through that series of steps is I can't introduce any new equation in my analysis. I can look at what he's done. I can offer what I've done now, which is a equivalent statement. So it's not a new statement, it's an equivalent statement, and we did the derivation. So that I can do, but the other stuff I can't do. Otherwise, people will say, that's not what Einstein did, so there's the door. The argument we went through today, though, is all found in his paper, right? So all those equations we've worked at, minus the T and S's. He doesn't use T and S's, but he does use T and the tau equation, the equation for the average for xi, all of that is in his paper. So you can, going back to your question, you can objectively determine if what I've said is accurate or not. Now, where it gets hard, in all honesty, is when you layer belief, right? I see what you said, Steve, but I choose to believe that you're not right. You haven't convinced me that there's anything here. I don't have control over rewiring someone else's brain. But what I can say is we've put 5 things on the table. I think I've addressed all 5. If I haven't, let me know which one I haven't. And if there's a 6th I now need to address, then tell me what the objective criteria is. Objective meaning fair to me and fair to you, so that I can then come back and present that to you, right? So the way I've interpreted it is, what's wrong? What's the root cause? Why haven't someone caught it before? Why does it work? Where does it fail, right? And so we've looked at what I feel were kind of 5 criteria to at least be able to knock on people's door to have the conversation that you're saying, and I agree with, the conversation that we now need to have.
Oh, go ahead.
I think that it's really, really smart what you're saying here, and I hope people are really keying into this, because we have a lot of people who come to us. I mean, we get emails constantly from people with new theories and how the mainstream's wrong about this, that, or the other thing. And I think what you've done here was staying inside of something that you do actually have a voice in, right? Inside of this computational science. I wouldn't have found out about your work if I hadn't seen this headline about using Chat GPT to challenge Einstein's equations, right? That's clearly a really, really smart way of going about it. And, you know, I personally resonate a lot with this. One of the projects we work on, and we're actually writing a book about this right now, is trying to do material interpretations of the atom. So quantum mechanics, and trying to make material sense of the atom and how it does all this magic, like light and gravity. And I kind of got into that because my background was in elastic mechanics. And I started to realize that a lot of the mathematics of resonant elastic mechanics were identical to many of the foundational wave equations in quantum mechanics. And then I started going around to different physicists, because, you know, one of the reasons I was excited to go to grad school at Columbia was because there's some great physicists there. And I got to know a number of them, and I thought these guys would have the answers. You know, I was like trying to really understand what the heck is going on physically in terms of these equations. What do they mean? And nobody had the answers. And so I think that's there's 2 things there. It's like, when you realize nobody has the answers about something that you're really curious about, that's a really good sign. And 2 is thinking about your particular tiny little knowledge base that you know a lot about, and how that might help plug in some of the holes in that thing that you're curious about, however small or large, right? I don't have to solve every problem about the atom. I just have to, you know, maybe put in one little thing that I'm sure makes a lot of sense and could be useful. And then, like you're saying, other people can come along and see this and build on top of it, apply it to new problems, start thinking about things in this completely different framework. Because I didn't go through the Mathematical Physics Institution and learn these things foremost. I went through elastic mechanics, right? My PhD was fundamentally a material science enterprise. And so I was thinking about it in a totally different way. And so I was privileged to this, albeit tiny little world, but it might have some help too. And I think that there's so much value in coming at it from an outside perspective that also has some credibility in its own, in your own record in that sense.
That's right.
I just think that's really, really smart. And I hope more people can grab a hold of that method. I think that that's super, super valuable in terms of fueling a paradigm shift. And it might not happen in your day, right?
Right.
And you have to have to surrender your ego a little bit and realize that science sometimes takes centuries to unfold. But if you love understanding nature and you really genuinely are committed to the human project, it's like, who cares? You're just kind of playing your part in the bigger game.
That's right.
I think that there's a tremendous amount of politics in science and in theory making that when you start out as a novice and you're going through a graduate program, it doesn't make sense because I think that most people believe that if they have a good idea and they tell it to someone, that person will see the quality of their idea and that the red carpet will roll out, the floodlights will come on, the angels will sing, and standing ovation in every room you enter for the rest of your life. And it is heartbreaking when you discover that isn't the case. And you realize that the art of scientific myth-making is a really people-centric process.
Very much so.
Yeah, and your discovery that there might be something wrong or something more happening here or a cooler way of looking at something, that's the starting line of the marathon that you have to run.
And everybody thinks it's the end. They think that I've discovered it. What more do you want? Publish it in Nature already.
Right. And I think people get confused. They look at someone like Einstein, they're like, wow, he's famous because he had a great idea. And it's like, no. He's famous because he was a really, really good networker. He was really good at filling in all of the blanks that he needed to contextualize his new understanding.
And he had a booster. He had Eddington, right? So Eddington was one of the biggest science writers of the day. And Eddington translated all of his stuff from German, figured out how to put it into readable, understandable English, and popularized him. He had a booster that basically whose job was to make him super popular. He was good at it.
And not to mention all, like we were talking about earlier, the mathematicians he was collaborating with, right? Because he needed to be able to say these ideas and translate them. So there's just such a human element to getting your idea into the world. And honestly, I consider him to have had a lot of luck in that he was in a place and time where the mechanical approach was failing, right? That's why we've been talking about all these interferometer experiments, is that they couldn't find this freaking ether anywhere. And so he was kind of poised at this great moment where he could just provide a solution that allowed them to move past the ether. That he's like, don't worry about it. We don't have to talk about it anymore. We don't need it. So yeah, what a constellation of interpersonal dynamics, society, the readiness of the moment.
The readiness of the moment. So that's something that I think about a lot because I think that right around the time of the turn of the century, there was this heady feeling of the limitless potential of humans, the death of the old world gods, and the belief that magic still might exist, but it now lives in the world of science. So you have these things folding together where technological progress is on the upswing fast enough that people really believe in it. The science is getting weird and it's getting popularized. It's the first era of these massive public interest research programs. I think that Eddington's model of the sun was published in the New York Times before it was published scientifically. So the popular science press was just starting to get going in this way that had never been seen before, because before you had the Royal Society and you had all these scientists exchanging letters, but it was never moved to the public in such a way as, behold what science can do for you.
Yeah, exactly.
And that kind of magic, I think, is what allowed Einstein to become so popular, because it's so fun and cool. His Gedanken experiments and paradoxes and people aging at different rates, and we're going to go to the stars one day and we're going to find all these crazy things. And so I wonder if you ever feel like a party
Not
pooper.
to mention black holes and big bangs.
Yeah,
and
yeah.
just
All of it all
sorts of
together.
supernatural wildness.
But my question still stands. Do you ever feel like a party pooper?
I do. Whenever this stuff comes up, we were at a party last night, and I had to cut myself off at some point. I'm like, don't do it. Don't get into this stuff. People want to talk about all of this. They love the magic, right? They love the black holes and the broken physics and the paradoxes, and the suggestion that it might not be necessary is just such a downer, I feel like.
Well, it's a game changer. But what I'm also finding is people are willing to have conversations and sometimes willing to dig a little deeper. So I have a friend who was at the time a PhD student in either astronomy or astrophysics or something at Cal Berkeley. And we got into a debate in my living room about whether or not Einstein said something in his paper. And I said, it's not in his paper. He doesn't say that. I've read it enough times to know what he says. It's not there. And he goes, no, but this is what he's talking about. So I ran upstairs, I printed off a copy, and I came downstairs and said, here's his paper. Show me where it's at. And his comment back to me was, in all of my years of advanced studies, I've never read Einstein's original work. Can I keep this? And I think that there's a large amount of that's at play, right? So I'm not saying, if you go through an undergrad, maybe you read his original paper. If you're going through a master's or PhD, depending on what you're focused on, maybe you read his original paper. But if you do it once. And you've probably bought into the fact that 100 years, people have said it's right. 100 years, experiments. I'm going to scan it. I'm going to move on. I'm going to do my research, right? It wasn't what he was focused on. So why should he go do a deep dive in this? Unfortunately, there's this huge collection of knowledge, some of which isn't even what Einstein said anymore, that is now out there that people are grasping onto. So we have to, that's why for me, it's important to talk about his paper, not just what your physics textbook on your bookshelf says about the theory. It's also important to just redo some of the calculations by hand. Outside of the partial differential equation, which you don't need because we now know it's an average, you can do all of the rest of his math using algebraic substitution. So you can do all the math by hand. So coming up and kind of getting your hands immersed in it is what I think is so important for any conversation. And for me, one of the things I learned was, again, that credibility piece. So is if I'm going to tell a story, can I make an interesting story that marries kind of some of these findings from AI with some of these findings from physics and kind of brings them together to tell an interesting story to a broader community? So ideally something interesting to my community of computer science and AI, but hopefully something that's interesting to a broader community as well.
And you published that in a computer science journal?
That's right. So it's called Discover AI. It's a Springer journal. And so interesting story. So a lot of times, especially if you're challenging the paradigm, you get shot down pretty quickly when you send your work out to a journal for review. And my first paper I sent out to a journal and they said no, but the journal editor said, I really would like to see you get this published. Try this other journal. So I tried this other journal and they said no. Mostly, and when they said no, it's because of aim and scope alignment. And he said, but I'd really like you to get it published. So try this other journal. And that's what landed me at Discover Artificial Intelligence. It's because I had received no's, but I received no's from people who wanted to see the work published. And to me, that speaks a lot to those editors because they could have just said no and not done that extra step to help me find a place for my work.
That's really wise. Yeah, that makes me think that in terms of the work we're doing on the atom, that some sort of material science journal would actually be a lot more appropriate than trying to go for the physics community directly head on. That's really wise.
I wanted to ask about implications because something that I tied directly to Einstein and special relativity and the spookiness of quantum, which I think is, I cannot clearly relate to the two of them, but I think that they can be, the threads can be linked to show how the rise of the Gedanken experiments and the acceptance of these paradoxical things then led to the opening of the mind for the acceptance of the paradoxes of quantum physics, have now led us to the point where we now question whether or not reality is real in a lot of cases. Do you know what I mean by that?
Mm-hmm. Mm-hmm.
And I wonder if you have thoughts about that. I don't want to lead you too much in that direction, but I just wonder if you have thoughts on simulation hypothesis, on the idea that we live in a holographic universe, on the question of what is foundational, is it mathematics or is it objects, materialism versus mathematicalism. I don't think that that's coined yet, but if you give me liberty to say so.
So this is one of those cases where I'll say, I don't know, but it's fun not knowing. And here's why I say that. The question you just asked about, are we in a simulation or not, is a conversation, probably an hour long, maybe an hour and a half conversation I had with a neighbor about 4 or 5 houses down. So we're talking about stuff. We're both ham radio operators, and so we have a couple of bonds that pulled us together. And he said, I want to just get your thoughts on, are we in a simulation or not? And we kind of went back and forth on that. And ultimately, I said, given what we know now about science and the world, we don't know enough to know if we're in a simulation or not. So if we are, we need to figure out what are those foundational questions that we need to ask ourselves that would help us answer that. And
I get the feeling that the presence of the ether makes simulation hypothesis less likely.
so what it does do is it helps to remove some of the spookiness, right? So 2 things that I think it could help to remove. One is the double slit experiment, right? Where you get all these waveforms and they kind of have these kind of quantized patterns. That can also be explained through pilot wave theory. So, which not my theory, it exists. But you can see those, you get the interaction of 2 waves. And, in the middle, it was the wave at time t and time t interacting. And over here, it was one wave at time t, but it's another wave that was at time t plus 2 or something
like
like
an
that,
out of
right?
phase wave, yeah.
So you're getting the interaction of different waves depending on when they came from their emission source. So that's one potential alternative for the double slit experiment. Another implication, I'm going to go back to the bus example with my niece. Notice I said, and I was very quick when I said it. I said, the bus can't go faster than my niece. And Charlotte's velocity, we used her name, her letter was C. So in mathematical terms, the bus, or the moving system, cannot go greater than C. So there's 2 things to note here. Number one is, in my equation, C is just the velocity of whatever it is I'm observing. So if it's Charlotte, then it's 1 speed. If it's sound, it's another speed. If it's the speed of light, it's another speed. If it's a yet to be discovered quantum medium, that's maybe faster than the speed of light, it's another speed that can go all in there. The other thing that's important to note is the constraint. The bus can't go faster than Charlotte, because if that happens, Charlotte can't make that first leg. And if Charlotte can't make that first leg, she can't turn around to do the second leg. I can't do the math. But we all know that a bus can go faster than my niece. Right? So we have to recognize that the equations are constrained by what we're asking it to do. It doesn't necessarily impose a physical reality constraint, right? It's a constraint because of what we're trying to answer. So 2 things. One is it lifts the constraint, about the speed of light, for example. And it also opens the door to a faster than light medium, which I think goes back to way back when I had three Steves and a Gianni as a company sitting back and eating lunch, where we're now saying, can we do, kind of real-time control of spacecraft that are out near Pluto or beyond? If you have a faster than light medium, that's now possible.
But it wouldn't be light, I guess, at that point.
That's right. It would be a different medium that would, a quantum medium or a gravity medium or something that's not electromagnetic.
Something extremely stiff. Yeah.
Something extremely fast. Definitely.
Yeah, well, I'm just thinking about like waves in a medium. The stiffer it is, like the faster they'll travel. So, like, I remember reading an interesting experiment Einstein did where he was like imagining he had like a perfectly stiff broomstick, and if he turned one end, would it instantaneously turn the other end? And I remember reading him musing about this at some point, and that really got my brain geared up about the possibilities.
Yep. There's a lot of fun puzzles like that to think about. It's it's one of those things. I think if you're a scientist, whether you're a paid scientist or an unpaid scientist or an amateur scientist, if you just marvel by these types of questions and you love asking them or answering them and you muse over them, I mean, if that's who you are, then more power to you, because it's the type of thing I find fun. I'd rather do this than go play golf.
Yeah. I mean, I think there's like I do want to talk a little bit and get your thoughts about the importance of reality being understandable, because this is what worries me about the simulation team, is that I feel like there is some undercurrent of shirking responsibility involved, because if there's no free will, if everything's computationally assigned and deterministic, then, well, I don't really have to, make my bed in the morning because like it was already computationally assigned that I didn't do it. And so it kind of takes the onus off people to take control of their world. I mean, one of the most powerful changes that I made in my own life ever was realizing that the future very much belonged to my actions. Like, I really could decide what's going to happen within bounds. Like, I'm not going to be able to levitate off the ground, but I can make a lot happen in 5-10 years from now in terms of changing who I am and what I do in the world. And I feel like all this spookiness and non-causality fuels, I hate to say it, but like kind of fuels laziness in people in a way. It kind of takes the realism off people's shoulders. And it's, I don't know, it's a little bit of a half-baked conception. I haven't really written about this or anything, but I'm curious if how that sits with you.
I think that to add to that a little bit, in addition to there being this hands off the wheel sort of mentality where the universe will just do what it does, there's also on the level of the scientists that are proposing these theories a lack of obligation to make things understandable.
Yeah, I forgot to mention that. That's the other side. It's like, it's disempowering when you stand at a physics class and someone is just like, you ask the question, you're like, well, how can this possibly be the case? That doesn't make sense. And they're just like, well, that's what the math says. Shut up. Like, put your hand down,
That's not a good teacher.
And this drove me crazy. When I was a little kid, I was just scouring the reference section of our library, trying to understand just basic, I was learning about relativity and string theory. And it just seemed like people weren't interested in making sense. And I think there's something really scary about that, because you can find yourself in an upside down world really quick. It's almost like an Ayn Rand objectivism type thing. It's like, no, there is objective reality, and it's important that you pay attention to it. Like, A does not equal B, and if you think that it does, then you're going to end up in a world of hurt. It's just not good for the world. I don't know. End rant.
I'd say I'm beginning to think about that question from a slightly different angle. And the angle that I'm beginning to look at it from is the large language model, Chat GPT model. And I'm going to play back kind of some thoughts from a speaker you had on your show. I want to say May 25th, but the date kind of escapes me. I think it was in the May timeframe. And he was talking about consciousness. And in that talk, he was talking about how consciousness is really about actions. And I thought, there's a lot about that. My wife always says, love is a verb, not a noun, right? So love is what you display, not what you say. I think there's a lot of truth in that. And so going back to this large language models, Chat GPT, if I say, translate this into Spanish for the first verse, French for the next, German for the next, and Japanese for the fourth, and it does it, is that intelligence or is that smart programming? I would argue that it's beginning to display intelligence because I didn't program it to do that exact task. So the fact that I can give it a task that I did not program it to explicitly do, to me, is a display of foundational intelligence. So let's talk about what we said earlier about that example. Roses are red, violets are blue. If we now understand how generative AI is constructing this next word, do humans do the same thing? When we're talking like we're doing now, do we begin our sentence with a word followed by another word, followed by another word? Or have we formed the entire thought or the entire paragraph and then we just play it out? It feels to me like we start talking and whatever comes out next is what comes out next. So there's some overlap. Does this mean that we've found how humans work? No. I think we're at the equivalent, and this is just my own bias and perception, that we're equivalent of the Wright brothers, right? So they learned how to fly probably before we had a complete discipline in aerodynamics. And I think what we're doing now is we're learning how to do these models like Chat GPT and GPT-4 and all the other derivatives that are out there now before we have fully understood the, call it, discipline of intelligence, whether it's human intelligence or artificial intelligence, to the same degree, call it intelligence dynamics, or like you call it aerodynamics. Once we understand intelligence dynamics and we have a discipline around it, then we're in a much better position to not understand how we behave and act and how these agents behave and act, but I don't know. Maybe it helps answer that question. Are we in a simulation or aren't we? But I think where we're at in terms of, even though we say this is great advanced technology, I think we're just at the beginning still. And there's a long road ahead of what I hope will be fun discovery.
Mm-hmm.
Yeah, that's a beautiful way of looking at it, really. And honestly, the way that you explain things is incredible. It's very smooth, and you give a lot of examples, and the way that you lay things out linearly, it's almost coded. Your explanations are almost coded, and I really appreciate that. Man, we're actually, I want to invite you to our conference next year, by the way. We're having our first DemystifySci conference in Austin, Texas in April of next year. So if you're around, I would love to find a way to get you out there and give a talk, because I think what you're doing here is just somehow immediately resonant with the entire purpose of our project, which is finding integrative, constructive ways of moving the needle in things that seem frozen, right? A lot of science, a lot of economics, the let's say state crafting, everything about our society seems frozen because we've gotten these things that work. They sort of work, and that there's a lot of argument for just sticking with the things that work. But of course, there's all these little fractures appearing under the surface. And so if there's one thing we are trying to do with this project, it is to explore those little fractures and see how we can improve things. And the way that you've gone about it is just so socially healthy, and it seems effective too, right? Like I said, I found your paper on Google News or something, right? That's incredible. How many papers do I find on Google News, right? So especially challenging some long-held theory as, pious as the Einstein equations or something. So yeah, I would love to interact with you some more, and I would love to share your work more with our audience. And
Welcome that. Thank you.
Yeah, and at the very least, I hope we can get together and have coffee sometime. We're down here in the Bay Area a lot, so.
Oh, absolutely. Yeah, absolutely. I would welcome all of the above.
That's
Awesome.
fantastic.
We'll be in touch then.
But before we let you go, can you tell us what you're working on next? Because it seems like you've wrapped this project a little bit and now you're moving on to something new.
So I am. Right now, what I'm doing is I'm trying to evaluate large language models and really kick the tires to, so I'll back up. When we talked about large language models earlier, we talked about this idea of trust. And so when we think about trust, there's kind of a four square grid. So across the two rows, one would be, I know the truth. And below that would be, I don't know the truth yet, but I'll know it in the future. And then in terms of the two columns, one is the LLM is going to tell me the truth, or the LLM has told me something incorrect. Right. So in the first quadrant, where I know the truth and it tells me the truth, I'm happy because it gave me the truth. I get more trust out of it. If I know the truth and it told me something was wrong, if I can't tune it by new prompts, then I'm going to be disappointed and I'm going to lose some trust in it. Ideally, I can get it to the right answer through prompt engineering. The bottom row is where it gets risky, because if I don't know the answer, I don't know yet if it's told me true or false. So if I trust it and it was truthful, then I'm happy and I will give it a few more trust points. But if I trusted it and I later found out that it was wrong, I'm going to hugely distrust it, to the point where I may not want to use it again because it's so untrustworthy, especially if it embarrassed me or otherwise cost me. So part of my research is to see, is there a way of evaluating large language models to help determine more in that trust quadrant, so that as people are interacting with it, we are interacting with something we trust more. So can we elevate it from being a junior first year graduate student co-collaborator to someone who's a postdoc that was one of our students? I'm saying that like I have a PhD, which I don't yet, but saying it like, one of our students that we have full trust in. So can we elevate these large language models in that way? So the research I'm doing right now is looking at LLMs that way. And to the extent that I can still layer in kind of looking at some of these relativistic ideas, or I'll call it moving systems ideas, then I'll layer that in as well.
I love that, because that's actually one of the big reasons that I've really decreased my usage of Chat GPT, is that it just hallucinates so badly, especially in these edge cases where you're asking it to really start thinking about scientific theories where there's maybe not a ton of primary material that it can draw from.
Right.
It just doesn't make a whole lot of sense. It'll just make stuff up. And so it's very difficult to rely on it because, like you said, you have to have something that you can trust and just take and move on from, or you might as well just do the work yourself. So I think that's very useful work. It's very cool. It'd be good to catch up down the line and see how that's going. So we'll
Yeah, absolutely. I would love that.
Do you have any closing thoughts?
Oh boy, this has been a really good conversation, and I'm thankful that you guys found my work, and we've had a chance to get to know each other for a little bit previously, but then have this conversation today. I hope that through the conversation that maybe it inspires a few people to just go look at Einstein's original paper, break out Wolfram Alpha, their calculator, a piece of paper, and just objectively see if the things I said made sense or not. And it doesn't mean you have to change your worldview. It doesn't mean you have to change anything you believe in. Just say, does it make sense? And then noodle. And if it sparks some new ideas for you, see where those new ideas take you, right? A lot of research, regardless of what you're doing, is saying, that's moving over there. I wonder why. And go over there. So if anything that we've talked about today inspires you to go over there and see what's going on, then go over there and see what's going on and have a lot of fun in the journey. So hopefully that inspires people to just do good things and go from there. So, but once again, thank you for having me. I really appreciate the opportunity to talk to you and your audience.
Thank you so much. Thank you for your ideas, for your work, for your enthusiasm. We'll definitely talk again soon.
Cool. Okay. You guys take care.
All right, take care. Bye, everybody.
Bye-bye.